Welcome to our series on advanced wave mechanics. Today, we will explore how waves behave when sources move, how they reflect off boundaries, and what happens when opposing waves collide to form stationary patterns. We'll begin by analyzing the Doppler effect, a fundamental phenomenon where relative motion alters the perceived frequency of sound and light. When a sound source moves relative to a stationary observer, the observer perceives a shift in pitch. If the source moves away, each successive wave crest is emitted from a position further back, stretching the wavelength and lowering the apparent frequency. Conversely, an approaching source compresses the wavefronts, raising the frequency. Mathematically, we express this using the source velocity, Vs, and the speed of sound, V. Let's apply this to a fascinating scenario. Imagine a whistle emitting a 500 Hz tone, moving away from you toward a flat wall. You will hear two distinct frequencies. First, the direct sound from the receding whistle, which is shifted lower. Second, the sound reflecting off the wall, which acts as if the source is approaching, shifting the frequency higher. The interference of these two waves creates audible beats at a rate of 4.4 beats per second. Moving beyond frequency shifts, let's examine how waves behave inside musical instruments. Whether we look at a bowed violin string, air vibrating inside an organ pipe, or a metal rod struck with a hammer, the fundamental mechanism is the same. An initial wave travels to a boundary, reflects, and travels back. This creates two identical waves moving in opposite directions, which is the exact recipe for producing a stationary wave. To understand how stationary waves form, consider a progressive wave hitting a solid wall. Because the boundary is fixed, the air particles there cannot move, forcing a 180-degree phase shift upon reflection. As the incident and reflected waves pass through each other, they continuously interfere. At certain moments, they cancel out completely. At others, they reinforce one another, creating a wave pattern that appears to stand still. This standing pattern contains distinct regions. The points where the medium remains completely stationary are called nodes. Exactly halfway between these nodes are the antinodes, where the particles vibrate with maximum amplitude. The distance between any two consecutive nodes or antinodes is always half a wavelength, while the distance from a node to its nearest antinode is a quarter of a wavelength. This spatial relationship is crucial for analyzing resonant systems. It is important to distinguish progressive waves from stationary waves. In a progressive wave, energy travels through the medium, and every particle vibrates with the same amplitude but at a different phase. In a stationary wave, energy is trapped within the loops, and particles between adjacent nodes vibrate in unison, but with amplitudes that depend entirely on their position. Finally, let's look at the physical conditions inside a stationary sound wave. Where displacement is zero at the nodes, the air particles are squeezed together and pulled apart the most, resulting in maximum pressure variation. Conversely, at the antinodes, where displacement and velocity are at their peak, the pressure remains completely constant. Understanding these pressure nodes and antinodes will be key as we transition to studying the resonance of air columns in pipes. Continuing from our analysis of wave patterns in pipes, we can actually visualize these invisible nodes and antinodes. If we suspend a thin strip of paper with lycodium powder inside a sounding pipe, the powder violently agitates at the displacement antinodes but remains perfectly still at the nodes. Alternatively, using Lord Rayleigh's sensitive flames or small microphones, we can measure pressure variations. Since displacement nodes correspond to pressure antinodes, the flames flicker wildly, or the microphone registers maximum amplitude at these points. In our idealized models, we assume the antinode occurs exactly at the open end of a pipe. In reality, because the air outside is free to move, the boundary vibrations extend slightly into the surrounding air. This extra distance is called the end correction, denoted as C. Developed by Helmholtz and Rayleigh, it is approximately 0.6 times the pipe's radius. Consequently, for a closed pipe, the effective length becomes L plus C, while for an open pipe, we must add C to both open ends, making the effective length L plus 2C. Now let's explore resonance, a fundamental phenomenon across physics. Every physical system, from a springboard to the air column in a pipe, has a natural frequency at which it prefers to vibrate. If we apply an external periodic force at a different frequency, we get small forced vibrations. But when the driving frequency matches the system's natural frequency, the energy transfer is highly efficient, causing the vibration amplitude to peak dramatically. This is why a soprano singing the exact resonant pitch of a glass tumbler can shatter it. The shape of a resonance curve is heavily influenced by damping, which represents resistive forces like friction or air resistance. Without damping, the amplitude at resonance would theoretically become infinite. With light damping, the resonance peak is incredibly sharp and narrow, meaning even a tiny deviation from the resonant frequency causes a massive drop in amplitude. Conversely, heavily damped systems have broad, flat curves. This makes tuning more forgiving, but limits the maximum amplitude the system can achieve. We can demonstrate this acoustic resonance directly using tuning forks. If you hold a vibrating tuning fork over a pipe, the sound is normally faint. However, if the fork's frequency matches the pipe's fundamental frequency, the air column is set into resonance. The sound suddenly amplifies dramatically as a powerful stationary wave forms inside the pipe. In our next section, we will look at how we can use this exact phenomenon in the resonance tube experiment to precisely measure the velocity of sound. Let's begin by exploring the resonance tube experiment, a classic method to determine the speed of sound in air and the tube's end correction. When a vibrating tuning fork is held over the open end of a water-filled tube, we adjust the water level until we hear a sudden increase in loudness. This resonance occurs when a stationary wave is established. Because the antinote extends slightly beyond the physical top of the tube by an end correction, C, the effective length is L plus C, which equals a quarter wavelength. If we only have a single tuning fork of known frequency, we can use a longer tube to find the speed of sound without needing to calculate the end correction first. By lowering the water level further, we locate a second resonance position. At this point, the air column supports 3/4 of a wavelength. By subtracting the first resonance length from the second, the end correction cancels out entirely, leaving us with half a wavelength. This gives us a highly reliable way to calculate the velocity of sound. Moving from air columns to vibrating strings, we use a sonometer to study transverse stationary waves. The fundamental frequency of a stretched string depends on its length, tension, and mass per unit length, as summarized by Mersenn's laws. The hollow wooden box of the sonometer acts as a resonator, amplifying the sound so we can easily hear it. By adjusting the movable bridges or changing the hanging weights, we can systematically test how each physical parameter affects the pitch. To verify these laws experimentally, we can tune the sonometer wire to match a known tuning fork. We can detect perfect tuning by listening for beats or by placing a small paper wire on the wire. At resonance, the wire vibrates violently and throws the paper off. To verify the tension law, we keep the length constant and vary the weights, using an auxiliary wire to compare frequencies. Plotting our results yields beautiful straight-line graphs that confirm Mersenn's mathematical predictions. Melda's experiment provides a striking visual demonstration of stationary waves on a string. A light thread is attached to an electrically driven tuning fork. Interestingly, the behavior changes depending on the orientation of the fork. When the fork vibrates perpendicular to the string's frequency matches the fork's. But when the fork vibrates parallel to the string is slackened and tightened once per cycle, meaning it vibrates at exactly half the fork's frequency, producing half the number of loops. We can actually use a sonometer to measure the frequency of our alternating current mains supply. By passing the AC directly through the metal sonometer wire and placing a strong magnet at its midpoint, the wire experiences an alternating magnetic force. This force drives the wire to vibrate at the mains frequency. By adjusting the wire's tension until it resonates with maximum amplitude, we can calculate the precise frequency of the electrical mains using our fundamental wave equation. So far, we have focused on transverse waves in strings. However, if we stroke a stretched wire along its length with a rosined cloth, we excite longitudinal waves instead. The particles now vibrate parallel to the wire, producing a very high-pitched, piercing note. The speed of this longitudinal wave depends on the material's elastic properties, specifically its Young's modulus and density. This gives us a powerful acoustic method to determine the elastic constants of metals. To study sound propagation in solids, we can clamp a metal rod exactly at its midpoint. When we stroke the rod longitudinally, the clamped center is forced to be a displacement node, while the free ends act as antinodes. This creates a stationary wave where the length of the rod is exactly half a wavelength. By measuring the frequency of the emitted sound and the physical length of the rod, we can easily calculate the velocity of sound within that solid material. In 1868, August Kundt devised a brilliant apparatus to visualize stationary waves in gases. Kundt's tube consists of a glass tube containing a light powder like lycopodium. A longitudinally vibrating rod projects into the tube, sending sound waves that reflect off the far end. By adjusting the tube's length, we establish resonance. The powder is violently agitated at the antinodes and settles into neat, quiet heaps at the nodes. Measuring the distance between these heaps gives us the wavelength of sound in the gas.
Kunst's tube is incredibly versatile. Since the vibrating rod and the air column share the exact same frequency, we can set up a direct ratio between their wave velocities and wavelengths. If we know the speed of sound in air, we can instantly calculate the speed of sound in the rod. Furthermore, by combining this with the rod's density, we can calculate its Young's modulus, linking acoustic measurements directly to mechanical material properties.
One of the most important applications of Kunst's tube is determining the ratio of specific heats, gamma, for different gases. The velocity of sound in a gas depends on gamma, pressure, and density. By measuring the wave speed in a target gas, we can compute gamma. This ratio reveals the gas's molecular structure, such as whether it is monoatomic or diatomic. Historically, this very experiment proved that the newly discovered element argon was monoatomic, a major milestone in chemistry. We can also compare two different gases directly, using a double-ended Kunst's tube. Here, a single central rod drives vibrations into two separate tubes simultaneously, for instance, one filled with air and the other with carbon dioxide. Because the frequency is identical in both tubes, the ratio of the sound velocities is simply the ratio of the distances between their powder heaps. If we know the speed of sound in air, we can easily determine the speed in the other gas. To visualize two-dimensional stationary waves, we look to Chladni's figures, first studied around 1790. By clamping a metal or glass plate at specific points, this reveals complex, beautiful geometric patterns. Unlike strings or pipes, these two-dimensional modes of vibration are not harmonically related in frequency. Now, let us transition from sound to optics, where we find deep wave analogies. To understand how light travels, we define a wavefront as a surface where all points vibrate in phase. For a point source, these wavefronts are concentric spheres. As they travel far from the source, they flatten into plane wavefronts. We represent the direction of light energy flow using rays, which are always perpendicular to the wavefronts at every point. In 1680, Christian Huygens proposed a powerful geometric method to predict how wavefronts propagate. Huygens' principle states that every point on a wavefront acts as a secondary source of spherical wavelets. These wavelets travel outward at the speed of light in that medium. The new wavefront at any later instant is simply the envelope that touches all of these individual secondary wavelets. This simple model successfully explains how light spreads and bends. Huygens' construction beautifully explains both reflection and refraction. For reflection, incoming wavelets strike a mirror and bounce back, forming a reflected plane wave that obeys the law of reflection. For refraction, as a wavefront crosses from air into a denser medium like water, the wavelets slow down. This difference in speed causes the wavefront to pivot, changing its direction. This geometric slowdown directly derives Snell's law, proving that the refractive index is the ratio of light speeds. This speed of light prediction was the ultimate battleground between Newton's corpuscular theory and Huygens' wave theory. Newton argued that light consists of particles accelerated by an attractive force at a boundary, meaning light should travel faster in water than in air. Wave theory predicted the exact opposite. When Foucault experimentally measured the speed of light in water and found it was indeed slower than in air, Newton's corpuscular model was rejected, securing a major victory for the wave theory. The wave theory also explains dispersion and how lenses focus light. Dispersion occurs because different colors of light travel at slightly different speeds in a medium like glass. Blue light slows down more than red, causing its wavefront to bend more. When a plane wavefront strikes a converging lens, the center of the wave passes through the thickest glass and is delayed the most. This reshapes the flat wavefront into a converging spherical wave that focuses to a single point. We can mathematically describe lenses by looking at how they alter the curvature of wavefronts. Curvature is defined as the reciprocal of the wavefront's radius. A converging lens physically adds a fixed amount of curvature, 1/f, to any passing wavefront. This added curvature is what we call the optical power of the lens, measured in diopters. By tracking these curvature changes from the object to the image, we naturally derive the classic lens equation. To wrap up our journey through wave mechanics and optics, we've seen how stationary waves allow us to probe the physical properties of gases, liquids, and solids. In optics, treating light as a wavefront and applying Huygens' principle gives us a deep, intuitive understanding of reflection, refraction, and lens behavior. While wave theory reigns supreme for these phenomena, remember that modern physics beautifully unites both wave and particle descriptions to fully explain the nature of light.